Hi guys, so today we're going to talk about section 8.3, geometric sequences and series. So geometric sequence is different than arithmetic sequence because instead of adding the same consecutive value, the common difference, for geometric sequence, the ratios are the same. Ratio meaning we're now multiplying your first term to get your second term, and that same common ratio, which we're going to refer to as R, is the same throughout the sequence. So for the first example here, 2, 4, 6, 8, to go from the first term to the second term, you are multiplying by 2 times 2 times 2. So our common ratio R is, let's say, 8 to the second term divided by the first term is 4 over 2, which is 2. So our common ratio is 2 for this problem. For the second example here, negative 1/3 to 1/9, and then 1/9 to negative 1/27. So if we do the same thing, R is A2 divided by A1, 1/9 divided by negative 1/3 is going to be negative 1/3 is our common ratio. Let's check. 1/9 times negative 1/3, negative 1/27. Negative 1/27 times negative 1/3 is 1/81. So the nth term of a geometric sequence is of the form the a sub 1 times your common ratio raised to the n minus 1 power. So think about it. Every single term is being multiplied by your common ratio. So your first term times by r. So a1 times r is your second term. Times r again would be r squared. Times r 4 times will give you the fifth term because it's your first term times you are multiplying by the common ratio 4 times to get to the fifth one. And then a sub n would be you're multiplying one less time than the nth place. So if you're looking for the 15th term, you would be multiplying your common ratio 14 times, the n minus 1. So notice here, your n plus 1 term, that would give you this, because n plus 1 minus 1 will give you just n. All right, example 2 here. Find the first 5 terms of the geometric sequence whose first term is 3 and common ratio is 2. So first term is 3 and your common ratio is 2. Your second term would be your first term times the common ratio 1 time, so that would be 6. A sub 3, your third term would be 3 times your common ratio 2 times, so instead of writing 2 times 2, it's just 2 squared, so that would be 3 times 4, which is 12, or just 6 times 2. All right, your first 5 terms, so do the next 2 for me. All right, so they are 24 and 48. So 3, 6, 12, 24, and 48 would be your first 5 terms of your geometric sequence. All right, next example. Find the 15th term of your geometric sequence whose first term is 20 and whose common ratio is 1.05. Take a few seconds and use your new formula you just wrote down and find the 15th term. So A sub 15. Quick reminder, PEMDAS, order of operations. We do parentheses and exponents before we do multiplication, so please be careful. You are raising the 1.05, the common ratio, to the 14th power first and then multiplying by 20. So the 15th term of this geometric sequence is 39.60. All right, next example. Take a minute to read this and make up a game plan for how to solve for the 9th term. All right, so what we're going to need our common ratio. So we're going to need to find R, and then we're going to need to find a sub n. And then once we have that, then we'll look for the 9th term. So what is the common ratio? Common ratio is 40 divided by 5, which is 3. A sub n, first term, times your common ratio raised to the n minus 1. There's nothing else you can simplify there, so that is your... There's nothing else you can simplify that there, so that is your formula for A sub n. The ninth term we are plugging in. So the ninth term, you're plugging in 9 for n, so go ahead and do that. So the ninth term is 32,805. Alright, finding a specific term given two terms that aren't the first and the second, but actually two random terms in your geometric sequence. So the fourth term, so A sub 4 is 125, and A10 is 125 over 64. So the 10th term would be the fourth term times your common ratio. One time would be the fifth term, sixth term, seventh term, eighth term, ninth term, 10th term. So that would be the fourth term times r to the sixth, your common ratio raised to the sixth power. So go ahead and plug in what your 10th term and 4th term are to solve for your common ratio. So r to the sixth is 1 over 64. Good news is 64 is 2 to the sixth power, so the sixth root of 1/64 is 1/2. So your common ratio is 1/2. Alrighty, so to make some room here, I moved everything over. So instead of spending the time and coming up with the equation for what the nth term would be, instead, let's just think about how to get from the 10th term to the 14th term, because it's asking for the 14th term. Alright, so instead of going and doing an equation for the nth term and then plugging in 14, instead, let's think about how many you would need to get from the 10th term to the 14th term. So A sub 10 is 125 over 64. To get from the 10th term to the 14th term, alright, so the 14th term is the 10th term times the common ratio 4 times, or r to the 4th power, which we just said was 1/2. So go ahead and multiply this out. Keep your answer in fraction form. So the 14th term in this geometric sequence is 125 over 1024. Alright, the sum of a finite geometric sequence is this equation. Please write this down. Alright, so using that equation, we are going to find the following sum here. Alright, so notice this is A sub 1. Alright, so looking at this example, that sum when n is 1 to 12, let's write out the first couple of terms of this geometric sequence. Alright, this is the sum from 1 to 12, so your first term is 4 times 0.3 to the first, and we are adding all the way up to 4 times 0.3 to the 12th. So using our formula here, our A sub 1 is right here. Our r, our common ratio, is 0.3, and the n that we are dealing with is 12. Alright, plugging in our formula, that's what we would have there. Evaluating that, our sum would be approximately 1.71. Notice the rule for the sum of a finite geometric sequence. Our index starts at 1. So if this exact same problem started at n equals 0 to 12, please take a look at page 592 for how that changes the problem a little bit. There's an added piece to it. All right, so that was of a finite geometric series. So the sum of the terms of an infinite geometric sequence is called an infinite geometric series, or in short, geometric series. So if we were to look at our formula here, as long as our common ratio is less than 1, very important. Here is what our sum would be. This is the formula we just wrote down. Looking at this term right there, if r is less than 1, so think of a fraction 1/2. If you are doing an infinite sum, so n doesn't have an n, so n is going to infinity, that 1/2, I just made up a problem here, that 1/2 going to infinity. 1/2 squared would be 1/4, then 1/8, then 1/16, then 1/32, then 1/64, then 1/28. If you were to type in these problems in these fractions in your calculator, what would they be approaching? Well, the bigger and bigger the denominator is getting, the smaller and smaller the decimal is getting. So you're actually approaching 0. So as n approaches infinity, r raised to the n, as long as the absolute value of r is less than 1, that is going to 0. So the formula for the sum of an infinite geometric series, as long as the absolute value of r is less than 1, is that equation without r to the n. So in short, that numerator would just be 1. So the first term, a1 times 1, is just a to the first. So this is the formula here. Please write that down. Notice it's going on for infinity, so there is no ending point there. All right. Our formula is up top there. Let's look at our first example here. We have an infinite geometric series for part A here, and let's use the formula to solve that out. Quick check here. Our index is 0 for our formula, and our index is 0 here. So this raised to the 0 power is 1, so 4 times 1 is 4, so that is our a sub 1. It's going on for forever, so ... So plugging that into our formula, 4 over 1 minus our common ratio, 4 is 10. So the sum of our infinite geometric series is 10. Notice, make a big note here. If it's bigger than 0, it doesn't have a bound, so that would mean the series does not have a sum. Take a few minutes and try part B. That is a geometric series, an infinite one, so use your formula to come up with what that infinite series sum would be equal to. Our first term in our series here is 3. Our common ratio is 1. So plugging that into the formula here, we would get that sum, that infinite geometric series sum would be 10/3, or approximately 3.33. All right, last problem here. Take a minute to read this. All right, so you are depositing $50 every single month. So here's our formula here because it's compounded monthly. So that is our interest formula for compounded monthly. So if you are your first $50, when you plug that in, that is 24 months for the 2 years to be compounded. So that first initial $50 you're putting in would be plugged into this formula for the 24. Your second month, when you plug that in, that would be raised to the 23rd because it didn't have the first month to collect that interest. So it has 23 remaining months for the rest of those 2 years, and so on. Your last payment, your 24th payment, would only have 1 month of interest attached to it. So if you notice here, all of these are the same. The only thing that's changing is these guys right here. So this is actually a finite sum problem of a geometric series because this that you're multiplying by is the exact same. So using your finite sum formula here with this information, plugging it in here, this is what you would get for your amount.